So this is when there is a very powerful way of thinking comes from. I mean, you're going to be learning this more, and we actually are not going to be able to completely cover this in this lecture. It's actually a pretty deep mathematical way of thought. It's basically think about differential equations called weakly. Okay, the name weakly doesn't really make much sense to start with in the first time I tell you. What it means is really thinking about the same differential equation but making less assumptions. Making weak means in mathematics, weak means less assumptions, like a weaker assumption, right? Okay, weakly means basically how can I think of the differential equation without actually assuming the equation is differentiable? So this is a pretty general way of thinking, but here I just want to give you a specific example of how to treat the differential equation more weakly. Okay, so we all know that if you take derivative of this, right? So let's say if you take a derivative of ddx of half of u squared, what do you get? Chain rule, right? Oh, if you take a okay, so let's say in general. So if you have a function f of u, and u is a function of x, right? If you take derivative of the function of u with respect to x, what do you get? Yes, you get df du times du dx. Great job. Okay. Now, one thing I want to say is that it doesn't make any difference if u is just a function of x or a function of x and something else, right? I mean, if u is a function of x and t, then f as a function of u is also a function of x and t. Then the partial derivative of f to u is the same, right? It's df du times partial u partial x. This context, it doesn't make any difference. All right. So just look at this and the term in the Burgers equation. We can see that if df du is actually equal to u, then the whole second term can be written as a spatial derivative, right? Okay, which means that in this case, my f of u should be u squared over 2, because if f of u is u squared over 2, then df du is equal to u. Okay, so then that means my Burgers equation is equivalent to partial u partial t plus partial x of half u squared equal to 0. Okay. Well, maybe you're saying, okay, here I'm still taking derivative here. What does it do to me, right? I mean, I'm still assuming just the half of u squared now is differentiable to x. I mean, it doesn't really help me that much. If half of u squared is differentiable to x, u should be also differentiable to x, right? But then the real important thing I want to do here is the following. Use red. The real important thing I want to do is the following. I want to integrate this whole thing over dx. Okay, I'm integrating the whole thing over dx over any interval a to b. if the differential equation is satisfied, which means du dt plus ddx of u squared over 2 is equal to 0 at every point x and every time t, then this integral over x should also be 0 at any time t and any interval a to b, right? So that means if I assume the differential equation is satisfied, then this equation, the integral form, is also satisfied. But the other way is not necessarily true. Even if the integral form is satisfied, I may not have the differential equation satisfied, because this integral form, as you are going to see later on, actually does not require u to be differentiable with respect to either t or x. So let's look at why that is the case.